Hi, everyone. I'm Marcel Verona from B-Move Media. I'd like to welcome you to this session. So we're going to be recording this. It'll be available to watch on demand afterwards. If you have any questions, please add them to the Q&A. That tab is on the right side of your screen. These questions will be sent privately. So with that, I'd like to introduce our speaker, Matthew Moore, application engineer from ZIVAN, who will be speaking today in the session, Charging Ahead, Adapting to Emerging Battery Chemistries. Welcome, Matthew. Please take it away.
Thank you. Hello, everyone. Yes, welcome to Future of Electrification 2025, and thank you all for taking your time to be here today with us. First, let me introduce Zappi Group as a whole. Zappi Group was founded in 1975 by Zappi, our motor controller company, and ZIVAN chargers were later introduced in 1983. Zappi, as well as ZIVAN, have headquarters in Italy, and ZIVAN has a 4,000 square meter manufacturing facility there. In just 2023 alone, ZIVAN produced over 60,000 chargers. And in collaboration with Delta Q, another one of our charging companies within Zappi Group, we offer and cover the ranges from 350 watts up to 36 kilowatt. As mentioned, my name is Matthew Moore, and I'll be your speaker today. I am an application engineer working with ZIVAN, and my main focus is to strengthen customer and business relations in North America, as well as collaborating closely with the R&D and sales teams back in Italy. Batteries have played a crucial role over the years in electronics, electric vehicles, and renewable energy storage. In this presentation, we will explore some of the key battery types, emerging battery chemistries, and battery and charger interactions. So how do batteries work? Many of us know that the battery is a storage of energy, but how does it do that? Batteries store energy within a chemical reaction between the anode, cathode, and electrolyte, such as in the voltaic pile shown. Zinc, copper, and cloth soaked in salt water can be stacked to produce electricity. Early on, lead-acid batteries dominated, but they were heavy and inefficient. In 1866, the zinc carbon cell was introduced, and it had a solid electrolyte, which led to our modern day AA and AAA batteries. In more recent advancements, the lithium-ion has become widely popular for its improved energy density and life cycle. In future trends, solid-state and hydrogen batteries are on the horizon. These are promising improved performance as well as sustainability. Solid-state batteries are using a solid electrolyte instead of liquids and is offering a higher energy density, greater safety, and longer lifespans when compared to the standard lithium-ion. They are mainly being developed for both electric vehicles as well as many industrial machinery or non-road mobile machines. Hydrogen batteries or fuel cells generate electricity by reacting hydrogen with oxygen and emitting only water vapor. This means that they are a very clean alternative and ideal for high energy applications like heavy machinery. In conclusion, solid state and hydrogen batteries will drive the future of energy storage, making machinery more efficient, sustainable, and cost effective. Lead acid batteries were introduced in the 1800s and are commonly found in cars, forklifts, and other machines. The standard 12-volt battery is made up of 6 cells in series, each offering 2.1 volts. A forklift has a similar structure, but you're usually working with 18 cells or more in a single battery pack. To quickly describe the chemical reaction that takes place within this battery, the sulfate ions will react with the lead oxide of the cathode and the lead atoms of the anode, causing electrons to flow when the two terminals are connected, and of course, powering anything in between on that connection. These batteries can have sulfation, which is when sulfates break away and accumulate at the bottom of the battery. And once they're at the bottom of the battery, they are no longer a part of the chemical reaction. A desulfator or a pulse charger can resolve this by sending high frequency pulses to break up those sulfate crystals and allowing them to dissolve back into the electrolyte and go back into the chemical reaction. Lead acid was popularized due to its low cost, simplicity, and wide availability. They have a proven track record for durability as well as being recyclable. There are limitations, however, such as their heavy weight, low energy density, sensitivity to over discharging, slow charge times. They require maintenance to keep the fluid levels at an adequate amount, and they have shorter lifespans due to sulfation that we spoke about earlier, corrosion, and general degradation of components. These batteries are often found in off grid solar systems, medical devices, and backup power applications, with forklifts in the non road mobile machinery markets being a notable use case due to their reliability and affordability. Nickel cadmium and nickel metal hydride batteries operate similarly to lead acid, but with a different anode, cathode, and electrolyte. Nickel cadmium has the positives of having a higher life cycle, a better current discharge rate, a higher operating temperature range, resistance to overcharging, and faster recharging. The downsides to nickel cadmium are that it has the memory effect, which is where partial charges and discharges can lead the battery to forget its full capacity, and over time, there's capacity fade due to this. It also has a high self discharge rate and is less energy dense when compared to lithium ion. Nickel metal hydride versus nickel cadmium, the metal hydride is going to have a higher energy density, less toxic, and no memory effect. The downsides of nickel metal hydride are that it has a high self discharge rate, although there have been some lower self discharge versions created. It has a lower performance in extreme temperatures. It has a shorter lifespan when compared to lithium ion and a tendency to overheat if it's charged too quickly or incorrectly. Nickel cadmium is commonly used in power tools, emergency lighting, while lead acid may often be found in the smaller aircrafts. Commercial aircrafts prefer nickel cadmium batteries for their high durability and ability to handle large current loads. AGM and gel batteries are using a glass mat or gel electrolyte instead of liquid. AGM has the positives of being now spill proof, faster charging, less maintenance, higher energy density, and more durable than the lead acid batteries. The downsides to AGM are that they are more sensitive to overcharging and high heat. The slow charging can also lead to sulfation and reducing the battery's capacity over time. Gel is going to have some similar positives of being spill proof, lower maintenance, and also better deep cycle performance. The downsides of gel are that it needs a slower charge to avoid damage. They're not efficient with fast discharge rates, and they're also more expensive than AGM. When comparing the two, AGM is best for high output applications in colder environments, while gel is better suited for deep discharge applications and warmer climates. Applications for both include forklifts, marine, light electric vehicles, and many other machines. Lithium was intended to replace the lead acid and nickel battery types and is now widely used in consumer products as well as electric vehicles. The cathode is made of an aluminum foil coated with a lithium compound such as lithium iron phosphate and an anode of copper foil with graphite with a porous separator in between to prevent short circuits. Lithium iron phosphate and lithium titanate are popular in NRMM markets for durability, long life, and operational temperature range. Lithium ion batteries last around 2 to 3,000 cycles, while lithium iron phosphate batteries can last even longer, up to 10,000 cycles. And these numbers can vary widely based upon the environment the battery is in, temperatures it's in, that sort of thing, as well as the amount of recharge and discharge. Lithium ion has the positives of being lighter weight, more energy dense, having a longer life and does not require the ventilation compared to these older technologies. Some downsides to lithium ion are that it includes thermal runaway issues due to the lithium dendrites, which can form during charging on the anode. And if they are able to reach the cathode, this creates a short circuit, which leads to thermal runaway and explosions. They also have a higher cost and recycling challenges. Furthermore, sourcing materials like lithium, cobalt, and nickel can be a challenge. So, next, let's delve into the exciting new world of emerging battery technologies. Lithium ion uses cobalt for stability during its charge and discharge cycles. This calls for concern for environmental sustainability, ethics, and supply chain of these batteries. This has led to cobalt-free versions being created, such as the silicon anode. The positives are that silicon, instead of the graphite anode, has led to a 20 to 40% higher energy density and 10 times the capacity for lithium compared to graphite. This could lead to EVs having 50% more range and charge in about 10 to 15 minutes, or an 80% charge in just 6 minutes. Current silicon batteries only have about 5 to 10% silicon mixed in with the graphite. But newer technology is leading to higher percent silicon and higher performance. The downsides are that silicon has a high volume of expansion during the charge and discharge cycles. This is going to lead to mechanical wear on the battery, and that means it's going to have capacity fade, conductivity issues, and in general, manufacturing challenges. Lithium sulfur is another option, with the positives of being up to 50% weight savings, up to 40% cost savings, non toxic, and twice as energy dense as lithium iron phosphate. The cons of this are that it has a low life cycle of about 1,000 cycles, and this is also due to the roughly 80% volume expansion during the charge and discharge processes. Researchers are still looking for a better solution as lithium ion is widely used in EV and NRMM markets, such as on forklifts, excavators, boats, and much more. Calcium ion uses a calcium metal, which is the anode, and with various cathodes, such as transition metal oxides and sulfides, are being researched. Unlike lithium ion batteries, which store the energy within their own chemical structure, calcium ion batteries leverage oxygen from the air as part of the fuel source. This reduces the reliance on scarce resources and improves energy density. The positives of calcium are that it is 2,500 times more abundant compared to lithium, as well as having a comparable energy density. The downsides are that it can be temperamental, so incorrect charging can cause inactive deposits, which leads to limited life and performance. Zinc air batteries are composed of copper and zinc as the anode, reacting with oxygen as the cathode in air. The positives of this are that the zinc air battery is cheaper, easier to excavate the components, also has chemically inert components, good energy density, and it is safer than lithium ion. The downsides are that it has a lower power output, the current electrodes and electrolytes degrade, causing shorter lifespans, and they can be a bit temperamental when it comes to ambient temperatures or humidity. The standard lithium ion battery creates a high demand for lithium, cobalt, and nickel supply. This demand brings concern for environmental sustainability, ethics, and supply chain of these batteries. China is already the biggest player in the lithium supply chain, and now they're building over 16 more lithium ion plants, which means they could potentially control over 80% of the supply. Lithium and sodium ion have very similar structures. Therefore, the transition would be fairly easy between the two with only minor production line changes. The positives of switching to sodium are that it is much more widely available, it's cheaper, and it's not explosive compared to lithium ion. On the downside, it has less energy density compared to lithium, a shorter life cycle, and lower voltage compared to lithium ion. For these reasons, the sodium-ion solution is not being adopted widely quite yet. Magnesium is another option, which has 2 electrons compared to the lithium's single electron. Double electrons means theoretically there's the possibility of higher and more efficient charge storage with magnesium ion. Similar to sodium, magnesium is going to be more readily available than lithium, as well as less explosive and more environmentally friendly. The downsides to magnesium are that it has an unreliable cycle performance, a low tolerance for voltage range, and a high cost, as it's not widely accepted yet. As the name suggests, solid-state batteries replace the lithium-ion liquid electrolyte with a solid electrolyte. This solves one of the largest drawbacks of lithium, which is that its electrolyte is highly combustible. Another interesting difference in the solid-state battery is that it does not have an anode, but just an anode electrical contact. This battery only uses lithium metal ions, which travel across the ceramic separator. The positives of solid state are that they have a higher energy density, faster recharge, and safer, less explosive due to thermal runaway when comparing to lithium ion. The downsides of solid state are that it's going to require more lithium. It's still combustible, although less likely than the standard lithium ion. Dendrites can still form and possibly lead to short circuits. It's also not widely available yet or used yet, and it has a higher price. Now that we've discussed the different battery types, let's revisit the applications they work best for. Lead acid is great for off-grid solar systems, medical devices, and backup power. And in the NRMM markets, it's great for forklifts, marine, golf carts, light electric vehicles, and aerial work platforms. Nickel cadmium is great for power tools, emergency lighting, aviation, and portable electronics. Nickel metal hydride is great for hybrid vehicles, rechargeable AA and AAA batteries, as well as home appliances. AGM is great for backup power for commercial buildings, as well as renewable energy. In the NRMM sector, it's going to be the same as lead acid. Gel is great for deep cycle applications, solar systems, mobile devices, and electric bikes. For the NRMM sector, it's going to be the same as lead acid. Lithium ion is great for consumer electronics, EVs, renewable energy storage, as well as drones. On the NRMM side, it's going to be all of the same as lead acid, as well as being great for construction equipment, robotics, mining machinery, tractors, and sweepers. Solid state, sodium ion, and calcium ion are all intended to replace lithium ion. Zinc air is great or is currently being used for hearing aids, sensors, and other slow drain devices, but in the future, it will possibly also be a replacement for lithium. The lead acid based battery types are using charging curves which are controlled by the charger. However, lithium ion based batteries typically use a BMS which controls the charge and communicates with the charger. We will discuss these further in the coming slides. The Battery Management System, or BMS, is a system capable of monitoring and managing the battery cells to ensure optimal performance and safety. The BMS functions include, but are not limited to, cell balancing to ensure all cells are equally charged, temperature management of the battery during the charge and discharge processes, state of charge and state of health assessments. It protects against overcharging, over discharging, as well as short circuits. J1939 is a set of standards for communication and diagnostic of vehicle components. This communication is based on control area network or CAN communication and has become a standard for many manufacturers as the language for electronic control units or ECUs. This communication uses parameter group numbers PGNs and suspect parameter numbers SPNs for standardized data exchange. The communication protocol between the charging station and the vehicle of the NRMM is regulated according to the corresponding local legislation. The J1772 is a US EV charging connector, which features both support for 120 and 240 AC charging. This plug offers up to 7.5 kilowatt single phase output. The EN61851 is a European EV charging connector, which features support for both 120 and 240 volt AC charging. Its plug offers up to 22 kilowatt three phase, and an important advantage of this Type 2 plug is that it supports a built-in locking system. The GBT 18487 is a Chinese EV charging connector, which features support for 240 volt AC charging as well, and also the plug offers up to 7.5 kilowatts single phase. These connector types have been widely adopted for public and home EV charging stations. These devices enhance the safety of the charging process by having the proximity detection pins as well as the control pilot pins, which send signals for safe and efficient charging. ZIVAN chargers work with both lithium and lead acid based batteries. ZIVAN offers charging algorithms for lead acid, and for lithium based batteries, there's ZIVAN's proprietary RE firmware, which also incorporates the standard J1939 as well as other customer specific communications. Our chargers offer different output and communication connectors depending on the customer machine's needs. In the following slides, I'm going to walk through a couple examples of how chargers interact with both battery types. The first interaction is going to be a battery that has a BMS and an EVSE, which communicate to control the charge. So in this picture here, we have an excavator being powered by ZIVAN CT 3.3 onboard charger, and it is connected to an AC charging station. To enter the charge mode, first the charger would be at idle. The AC plug is then connected. The MCU of the charger is woken up by the plug. The MCU and the EVSE negotiate. The EVSE activates the AC power. The primary and secondary CT 3.3s switch on, and the system is now ready to charge. To terminate the charge mode, first the charger would be charging. The operator would send a command to terminate the charge. The MCU negotiates the AC switch off. The AC is then removed and the CT 3.3 switches off. The MCU now unlocks the AC plug. The AC plug is then removed and the MCU enters idle mode. Termination is now complete. To enter traction mode, first the vehicle will be at idle. The EV wakes up the MCU via a KSI. The MCU verifies the AC plug state and system integrity. The MCU communicates results back to the EV, and now the EV enables or disables machine functions such as the traction or rotation, and now the traction mode is activated. To terminate the traction mode, the system is currently in traction mode. The EV is in work mode. The EV switches off the MCU by removing the KSI. The MCU enters an idle mode, and the termination is now complete. The next type of battery is one without a BMS, which usually are the lead acid based batteries. In these interactions, the charger controls the charge of the battery. Our chargers come with up to 7 charging curve options pre-installed for different batteries or preferred charging method. One of these curves is CU4, is fully customizable for the customer who prefer to control all aspects of the charge. Customization of this curve includes access to changing several parameters such as the current, voltage, and time of each phase. ZIVAN offers several offboard fast charger options, such as our MG line pictured here, which offers up to 36 kilowatts in a single package. All of our chargers can be linked in parallel for even higher outputs and faster recharge times. The charge curve shown is our charge curve 1, and it is designed for lead acid or gel type of batteries. This charge begins with phase T1, which lasts around 5 to 7 hours and is where the bulk of the charge occurs. In phase T1, the charger current starts out at maximum output and slowly tapers down, while the battery voltage increases rapidly. Once the battery voltage reaches U1, which is approximately 80% charge, the charger enters phase T2, which is the absorption phase. Phase T2 lasts around an hour, and during which the battery voltage remains relatively the same, while the charger current drops rapidly to I2. Lastly, the equalization phase occurs in T3 to ensure all cells are similarly charged. This phase lasts around an hour as well, and it ends with the battery being fully charged and the charger's current dropping to nearly zero. Compared to our CB firmware, which is what we just spoke about with curves 1 through 5, Archaea firmware has the same first 1 through 5 curves, but adds curves 6 and 7, which are designed for much faster recharge times. So instead of charging currents being in the first 5 curves around 7 to 25% in phase 1, in curves 6 and 7, it has been boosted up to around 40% during phase 1. So about double the current during phase 1. ZIVAN is also offering recharge rooms, which are designed to house many battery chargers in a single location, such as in a warehouse or a manufacturing plant. ZIVAN offers 2 systems for recharge rooms. The first is the Take Me system, which is a basic first in, first out system that helps to prolong the life of the batteries. This system utilizes a control box and an LED light system to prolong the battery life by showing which batteries are ready to be used. The second is ZIVAN's proprietary brain system, which utilizes an internal algorithm to assess the battery's state of health and pick the best charging curve for that battery. This system can have many chargers connected and can be monitored and managed remotely. Remote management includes remote flashing of software, charging curve changes, scheduling charge type based on the day of the week, as well as other settings. The TV displays will show the number of which batteries are ready to be taken off the charge and used. Both of these systems are typically designed for lead acid based batteries and help to prolong the life of these batteries. One of the pluses of this solution, much appreciated by many of ZIVAN's clients, is that ZIVAN oversees the whole process and service of recharge rooms. So there's no need for any third party integration. So, in conclusion, emerging battery chemistries such as the solid state sodium ion, calcium ion, and zinc air offer great potential for our future. And although they have great potential, there will definitely be some challenges in performance, lifespan, as well as scalability. But all of this can be overcome with the collaboration between manufacturers, OEMs, and the R&D teams. Hybrid solutions combining lithium ion with the emerging chemistries, along with continuous, will help to bridge this gap. Adapting production lines to these new technologies will definitely require some investment, but offers long term benefits. The future of batteries is very exciting, and with the right approach, we can unlock their full potential. Thank you all again for attending, and I will pass it back now for the live Q&A.
That's great. So we have a few questions here. Let's just start with this one. So this is about solid state and lithium and sodium ion batteries. What are the potential costs and scalability challenges that manufacturers may face when adopting these new chemistries?
Yes, that's a great question. So the magnitude of the cost and scalability can vary widely depending on the specific battery type we're discussing. To hit on some of the ones you just mentioned, the sodium ion would be a bit easier and cheaper as it has a similar structure to lithium ion. But the solid state batteries are definitely going to be a bit more expensive due to the materials and manufacturing complexity. And the scaling of solid state batteries is definitely going to be a little bit more difficult and still needs to be refined. But overall, no matter which direction you go, there's definitely going to need to be some significant investment in new production facilities in order to scale these new technologies.
Great. So just saw another one come in related to that. Do you have any thoughts on when we could expect to see mass production for solid state cells?
We are seeing it on the horizon. I don't personally have an exact date on when that would be. We could definitely talk about this more offline and talk to the battery manufacturers we work with and see exactly when they think that this could really be a possibility for us.
That's great. Okay, next question. What are the key innovations we can expect in BMS battery management systems to better integrate with emerging battery chemistries?
Yes, the BMS will definitely have to adapt probably to different voltage ranges, charge cycles, and energy densities. For solid state batteries, the BMS is probably going to have to manage different thermal profiles and potential expansion of the solid electrolytes. Um, Innovations are likely probably going to have to include more sophisticated charging algorithms, as well as real time monitoring and improved communication protocols.
Got it. Um, for how do environmental conditions like temperature, humidity tend to affect the performance of batteries and their charging process?
Yes. Either way, extreme temperatures, hot or cold, are definitely going to have some effect on the charge rates, the efficiency, and also battery lifespan. The higher temperatures are going to lead to more overheating and thermal runaway, such as in lithium-ion batteries. And ZIVAN actually prepares for this by having a battery temperature monitoring, and it will stop the charge and as well as alarm if the battery temperature gets too high. For the colder side of things, this is probably going to slow down the chemical reaction within the battery and reduce the performance. And humidity is also a factor here. It definitely can play a role, especially in some of the new battery types that leverage the air, such as zinc air batteries. Those will definitely be affected by either too high or too low of humidity.
And do you foresee chargers and charging systems becoming a bottleneck for fast charging in the future, especially for EVs as battery electrodes evolve to handle higher current densities?
I would say that it wouldn't necessarily be a bottleneck. I would say that as long as, the battery manufacturers are communicating with the charging companies and working with the R&D departments, it could possibly be a both coming out nearly the same time, having the battery and the correct communication for it. It's just really gonna be about communication between the battery manufacturers and the R&D departments for the charging.
Okay, this one's an interesting one. So for aqueous batteries, do you have experience managing the profiles to reduce water consumption?
If you're talking about, like, lead acid to reduce how much water consumption is happening, um, yes, yes, you can tweak the charging algorithms. As I said, we already have some that are optimized for lead acid, but also we have the CU4, which is fully customizable. And, as well as these being high frequency chargers, you're already gonna be getting, less liquid consumption, compared to the older style chargers.
Okay, so I think we're going to wrap up with the last one. Can ZVAN chargers handle both lithium ion and lead acid batteries simultaneously?
Xenon chargers are versatile and can handle both battery types, however, not at the same time or simultaneously. Switching between lithium ion and lead acid battery types requires a firmware change. And this firmware change is fairly easy to do. And if you were to need any help, you can always reach out for assistance from your local application engineer.
Great. So I think we're going to wrap this one up there. Everybody, thanks for attending the session. Please join the next one from the lobby. There's many more to come between today and tomorrow. And thank you, Matthew. Great presentation.
Thank you all.